Welcome to AGI's Earth Day webinar featuring speakers who specialize in the study and mitigation of microplastics pollution. Today's presentations will provide invaluable insights, strategies, and solutions to address this pressing environmental concern, empowering us all to take meaningful action for a cleaner, healthier planet. First, you will hear from Aidan Sharon, the director of End Plastics Initiative, about Earth Day's theme, Planet versus Plastics, and the many ways you can celebrate this year.
I just want to give a huge thank you to the American Geosciences Institute. I'm Aidan Sharon, and I'm the director of End Plastic Initiatives at EarthDay.org, the official organizers of Earth Day since 1970. The theme for Earth Day 2024 is Planet versus Plastics, to highlight the health risks associated with microplastic and their additive chemicals. The public is generally unaware of these health risks. Our mission is clear. We want to shine a spotlight on the dangers of plastic, both for our planet and for human health. We want to raise awareness about plastic. It's not inert, and every bit of it ever made is still on Earth. We aim to empower people with real knowledge, give them the information they need to make informed choices about how harmful plastics are and how best to mitigate their exposure. With informative campaigns, educational materials, and public outreach initiatives, we seek to bridge the gap between scientific research, so the clever stuff you do, and public awareness, ensuring that the true cost of plastic use is not overlooked. But awareness alone is not enough. As stewards of the planet, we are compelled to take action. This Earth Day, we rally behind a call to arms for reduction in plastic production. Together, we have the power to effect change, to shift the trajectory of our planet's health and safeguard the well-being of future generations. So, this Earth Day, join us in the challenge of Planet versus Plastics, creating a more sustainable world for us all. I hope your sessions go well today, and happy Earth Day.
Our next speaker, Dr. Maya McGuire, will offer a comprehensive overview of microplastics research, shedding light on our current understanding of the effects of microplastics on the environment, addressing common misconceptions about plastic pollution, and the areas where further investigation is crucial.
Hi everyone, my name is Dr. Maya McGuire, and I'm a faculty member at the University of Florida. I'm going to talk to you today about plastic in the ocean, and specifically what we do and do not know. Anyone who has seen trash at the beach, trash in the ocean, knows that a great deal of it is typically made up of plastic. But exactly how much? If you look in the published literature, you'll see values ranging from 45 to 95% of marine litter being comprised of plastic. That's a huge range, and it gives you an indication that this is something we really don't know much about. We do know that we make a lot of plastic. Since about the 1950s, the estimate is that we've manufactured 8 billion tons of plastic materials. We don't know exactly what's happened to all of that material. We think that some of it is still available and usable, some of it has been incinerated, and the rest of it has been discarded, might be in landfills, might be in the environment, or a small amount of it may have been recycled. If we look at this graphic, you can see some of the estimates for some of those fates. The blue line at the bottom is the amount recycled, and you see that that line doesn't really start to grow until sort of the early 2000s. And you have the same story for the incinerated waste. So this is perhaps in part why we don't really know the ultimate fate of all of the plastics that have been made since the 1950s. When we think about plastic waste in the ocean, we know that the vast majority of what ends up in the ocean is coming from land-based sources, and that a lot of that is making its way to the ocean via rivers. And a lot of these rivers are in third world countries. And it's easy to blame those countries for that waste generation, which isn't necessarily true, because you need to remember that a lot of our first world countries, until very recently, were exporting our plastic waste to other countries for them to deal with. And ultimately, that's where it ended up getting mismanaged and ended up making its way to the ocean. But that's not to say that we could do a much better job if we had kept that plastic in our own countries, because nobody's very good at dealing with plastic waste. So how much plastic is in the ocean? As I've hinted already, we don't really know the answer to that. And part of the reason is that there is no standardized methodology for sampling plastic in the ocean, regardless of the size of that plastic. You've got to remember that the ocean is huge, that there's a great depth in some places to the ocean, and that the ocean isn't just the water, it is also the sediments at the bottom of the water. And really, it is that entire water column, the sediments, and potentially the air above the ocean that would need to be sampled to try and come up with a figure for the amount of plastic that's in there. And one of the challenges is that different plastics have different densities and therefore will be found at different levels in the ocean, just naturally as raw plastics. Of course, as long as, or for the length of time that those plastics are in the ocean, they will have things accumulate on them. So they might get fouled by other organisms, and that can change the density, can either make them more buoyant or less buoyant. If plastics do sink to the bottom of the ocean, they can end up getting buried in sediments and kind of trapped there. If they get eaten by organisms, they can get excreted as fecal waste, fecal pellets that might have a different density than the plastic itself. And so there are all these factors that go into affecting where in the water column the plastics are going to be found. And again, remember, we don't have a standardized methodology for sampling that entire water column. You've probably heard of the things that we tend to call garbage patches. The Great Pacific Garbage Patch is perhaps the best known, but it's been found that there are garbage patches in all of the major ocean basins, resulting from our current system that tends to form gyres. And there's a bit of a misconception that these garbage patches are these large floating islands of trash, right? That's how they're portrayed in the media. But the reality is that's far from being true. While there may be lots of plastic in the water, it's not visible floating as a giant mass on the surface. Because of those different densities, because of wind and waves, those plastics get mixed in to the ocean. And a lot of those plastics are broken up into really small pieces. And so they are not visible as floating islands or patches. One of the other things we don't really know is how long plastics last in the natural environment. We can say that the majority of the petroleum-based plastics probably last for decades, if not centuries. But those plastics that are thinner, smaller, made from other products, made to be biodegradable or compostable, the length of time that it takes for them to degrade in the environment really depends on the environmental conditions. So where those plastics end up, the moisture, the temperature, the oxygen levels, the sun exposure, all of those things play a role in how quickly things do or do not degrade. So for example, in wet soil, PET bottles can stay around for 35 to 180 years. And at that point, they might break apart into microplastics, but not necessarily go back to their elemental compositions. In the ocean, those degradation rates are probably slower. We don't really know whether the amount of plastic in the ocean is increasing or not, in great part because we don't have that standardized methodology for studying the amount of plastics in the ocean. So are they increasing or not? We don't really know. We do know that microplastics are in the air, and this has been a subject of research, particularly in the last, say, 5 to 10 years. We know that the majority of these tiny plastics that are in the air are in the form of fibers, and this is consistent with the findings about microplastics in the ocean and other environments as well. The fact that microplastics are in the air further complicates studies related to microplastics in other places because we need really strict protocols to control for or account for potential contamination by these aerial fibers, right? Once again, we don't have a standardized methodology for that. There have been various recommendations that have come forth about the sort of level of control that needs to be made, the level of accountability. You need to have control setups that you then measure the microplastics in and subtract from your samples to account for that potential contamination. But again, this isn't consistently done, and that makes it really difficult, number one, to compare studies to studies, and number two, to actually figure out what the results of different studies actually mean. Did they actually measure microplastics in the organism or the environment that they had intended, or are the data skewed by contamination from aerial microplastics? So hopefully I've provided you with a little bit of information that you can use to help you judge the validity of some things that you might see in the media. At the very least, hopefully it'll make you ask questions about, well, how did they come up with those data? How was that study conducted? What kind of controls were there to account for perhaps aerial contamination of samples? We still have a lot to learn. We still have a lot to develop, but hopefully you now will be a smarter consumer of information about plastics and microplastics in the ocean.
Our next speaker, Dr. Melissa Lencheski, will discuss microplastics in groundwater and the urgent need to understand how these microplastics are transported and where in the environment they will end up.
Hi, my name's Melissa Lencheski. I'm a professor at Northern Illinois University in the Department of Earth, Atmosphere, and Environment. And today I'm going to talk about the fate and transport of microplastics in the subsurface, especially groundwater. Well, one of the reasons that I'm talking today about groundwater is that sometimes it's considered invisible. Of all of the liquid available freshwater on the planet, most of it is in groundwater. And because we can't see it, sometimes it is ignored. But groundwater is used in the agricultural sector, domestic use, and industrial processes, and so it cannot be forgotten. So the objectives today, I'm going to talk about the sources of microplastic and how they transport into our groundwater systems. Look at different properties of the microplastics, from their size, their shape, and their type, and how this might impact their transport. And then talk about some case studies of microplastics in groundwater. Well, microplastics can get into our groundwater in a multitude of different ways. So from our urban areas, our agriculture, we could be putting them in through our septic systems. We could be putting them in through managed aquifer recharge. Or as they move through our environment and they get into our waterways, they can go through our hyporheic zone and then transport their way into our groundwater systems, to later be abstracted back out into agricultural or drinking water supplies. And when we look at the soil particles themselves, we can see that maybe these shapes clog pores, maybe they slither through or get trapped within inside of there. And so we need to better understand how these microplastics move in our environment. One of the other issues that happens with groundwater is, how do we sample it? When we do any of the sampling from using monitoring wells, a lot of times they're made out of PVC pipe. Our balers, our equipment, our gloves, everything that we use in order to generally look at groundwater is made out of plastics. And so we have to be able to separate those out to be able to really truly understand what plastics are getting into our groundwater supply. In order to do this, a lot of times when we're starting to do these experiments, you're using all metal. So in this case, the groundwater is being pumped out and then going through a filter that's right in here. All of the tubing is natural rubber so that we can know what's truly inside of our groundwater versus what is just coming from our sampling equipment. So there's been a lot of experiments and projects that have been done around the world that have looked at microplastics in the United States, Europe. China has a lot of them, and Australia. So one of the projects I was going to talk about today was this one that was done in Australia, this case study in 2022. They looked at groundwater wells in an agricultural region and found microplastics ranging from about 38 microplastic particles per liter, and their size ranged between about 18 to 500, and they mostly found polyethylene and PVC within there. Other experiments have tried to, in India, looked at, could you predict if there's microplastics inside the groundwater by looking at other hydrogeochemical properties of the water. So they did it in an urban setting. They looked at a series of wells. They looked at them for their chemistry, and they couldn't find any correlation between the groundwater quality and the quantity of microplastics. Other projects in China have looked at the high abundance of microplastics in groundwater, especially in anthropogenic activity areas, so like major cities. They found a lot of polyethylene, which is generally water bottles, and polyurethane predominant in the groundwater. They found that more than 90% of the particles were less than 100 microns in size, showing that the smaller sizes are moving into the environment. Well, a lot of these projects all tell us that they are found in places, but how do they actually migrate or transport inside of our groundwater systems? Some experiments have been looking at that. They looked at microplastics, especially when they age. So as microplastics go from pristine to aging, just like our soil particles that weather, our plastics weather too. And their surface charges change at pH 7 to about to a negative charge. And so as these microplastics are aging, they increase their mobility because they're changing these surface charges that are on there. Also, if we have increasing ionic strength, so going from a monovalent to a divalent cation, or even concentration, that changes the amount of migration. That we have less migration, we have increasing mobility of them with, say, sodium chloride versus calcium chloride. Other experiments have looked at sand columns, especially with the smaller size particles, which we know migrate faster into the environment. But when we change the flow rates in here, going from 2.2 to 7.5 milliliters per minute, we increase how much plastics are coming out. We can also see that the larger sizes have less mobility, so we have to understand the shape and the size of them. And then the water salinity. So as we're seeing salinization, especially of our coastal areas, that could be that we're going to see decreasing outputs, so decreasing amounts of microplastic in there, and that microplastics are negatively charged with age. So I wanted to just talk about a few projects that we've been doing that we wanted to understand better about the transport of these. So looking at the size, the types, and the shapes of the plastics, and did control experiments. So in our experiments, we were looking at polyethylene, polypropylene, polyamine, and polyesters in sand columns. So these are, and I'll show you a picture of those in a second. We investigated how the microplastics transported into there, so their shape. So is there a fragment? So that's the pieces where they're kind of bumpy on the outside into there versus a perfect sphere versus a fiber, which is a straight piece. And then did mixing them together impact it? And then we wanted to measure if there was a change in the hydraulic conductivity with maybe clogged by these plastics. So we have a column here of stainless steel. We have an inlet beaker where we put known plastics and known concentrations of plastics into it. We pump the water through the column, and then we monitor how much is coming out the other end here. And we looked at different shapes and sizes of the plastics, and we tried to see if there was any variation in them. So these is our column experiments here in the lab. We did them in triplicate so that we could compare between them and get some statistics. We did a conservative tracer to be able to compare this to the water migration. We put in about 77,000 microplastics per liter, which is a lot of microplastics to put in compared to what we've been seeing in the environment. But this way we could really get at how much is being transported in there. And we did this over an 8-hour period of time. Since our experiments were controlled, we know what plastics we put into each of the columns. We could count just the plastics that are of that known type that come out, not having to worry about contamination in these. So these are the fibers, and it's hard to see, but these are the fragments. They're just chunks of the plastic that we had to make these ourselves because you can't even buy some of these plastics out there. So we had to make some of these ourselves. So we looked at what are called breakthrough curves to look at the transport of these plastics. So along the x-axis, we have 2,000 minutes. So the experiment starts at 0, ends at 2,000. Along the first y-axis is concentration. So we're looking at the number of particles we found per liter. Along our other x-axis, we have the sodium chloride concentrations, and those are in blue. So we know that the blue is how the water is migrating through there. And so a shift over of all of the plastics from the blue shows that there is retardation of the microplastics. And based upon these experiments, we could come up with the retardation factors for the microplastics. They range from 1.5 to 1.75, which is really important if we're going to do modeling of transport of contaminants. We need to know the retardation factors for all these different compounds. And so by having the different shapes and the types of plastics, we can start coming up with some factors that we can model this. The other thing that we noticed is if you look at the height of each of these columns, it varies depending on the type of plastic that was in there, showing how much of it was absorbed into the soil particles. So how much of it is actually retained into there. And so there is variations within these. So we're seeing differences in the concentration of it being absorbed into there. So different plastics are being retained more within inside of there. So we're seeing a lot more retention of, say, fibers versus fragments of the exact same plastic. We also did experiments where we did field experiments where we had wells 1 meter apart. We put in the polyethylene spheres, and then we counted how many of the spheres went through the system in order to see how they transport in a natural sand column. So this is all in sand. And what we did was, even though the plastics were, they looked uniform to us originally, we found that the transport really varied the sizes, that the smaller size particles were able to get through the columns a lot faster than the bigger ones. And so we really need to be looking at the shape and the plastic size in order to be able to look at transport. So in summary, our controlled column experiments understand the fate and transport of plastics. We really need to understand that. We know plastics are everywhere, but we really need to understand how they're migrating into the system. Microplastics are delayed compared to it, so we have retardation factors for these compounds now. That the microfibers, so the long, thin pieces, are retained more than, say, the spheres. And the larger size, so size matters, are more removed from the system. And that the type of plastic changes its migration. So we really need to be thinking about all these different factors when we look at our subsurface environments. So one way we can do this is with what's called a laser direct infrared imaging system. This is from Agilent. And in there, you put the sample onto a filter that's 0.2 micron in size. And then each piece of plastic, they take a picture of it. They measure the length, the width, how circular it is. It uses the laser to identify the plastic and also to give you a spectra so you can know about aging in there. And so that you can chronicle not just the size, the shape. You can say, well, okay, all the smaller particles are this particular type of plastic. Larger ones are this type. We're starting to see the spectra change. So we're seeing some weathering of some of these plastics. We can look at the shape. So we can say, okay, almost all the spherical ones are in a certain shape. And so this is where we're going to have to go with microplastic transport, not just counting them, but really understanding all of the physical properties and chemical properties of the microplastics. So with that, I just have some final closing thoughts on microplastics. So microplastics are everywhere. We know that. We've heard this with multiple projects and everything else that's going on in this world. But we really need to understand their fate and their transport. We need to understand how they're migrating, what is impacting them, so that we can have better models out there. We can use what is called colloidal transport theory, which has been around for a long time, but that only gets us so far. With the amount of plastics and all the different environments, we really need to expand that. Doing these types of projects is really tough because the equipment that we have is plastics. It's everywhere. We're working on building a laboratory for microplastics, and they're like, oh, it's easy to not have metals in there. But when we try to say no plastics, the architects are just going, I don't know how to do this. They stick to everything. So this is our pressure transducer, and this is everything. It just sticks to the glassware and everything. Another problem is microplastics float. They're less dense than water. And since they float in water, depending on how your well is located, if you're not screened over the water table, you might be missing some. Or if they're screened, the plastics might migrate up and you might miss them. So really understanding the well construction impacts how we understand where they are in the environment. We can't just report microplastics per liter. We need to start reporting the size, the shape, the type, the age of them. So are they aged? We need to be looking at blanks and samples. So we really need to move beyond just the number of plastics. Also, when we look at other types of contaminants out there, those are usually in milligrams per liter. Here we're doing particles, and that might change by the types of plastics that are out there. So column studies are one way to get at some of these things, but we really need some other experiments in order to be able to truly understand microplastic transport in our groundwater. And with that, I'd just like to say thank you for listening to me today.
Our next speaker, Dr. Scott Coffin, will discuss the negative effects of microplastics on human health, as well as how California is monitoring microplastics in drinking water and aquatic ecosystems.
Hi, my name is Dr. Scott Coffin. I am a research scientist with the California Office of Environmental Health Hazard Assessment, and I'll be talking to you today about California's adaptive risk management of microplastics in aquatic ecosystems and drinking water. In 2018, the California Water Boards received a mandate from the legislature to address microplastics in drinking water, including defining microplastics and adopting a standard method for monitoring, a plan for 4 years of testing and analysis, consider adopting a health-based guidance level, as well as accredit qualified laboratories for testing. The same year, California Senate Bill 1263 was passed, which requires the Ocean Protection Council and the California State Water Boards to initiate a statewide microplastics strategy by 2022. Included in the strategy is the plan to develop a risk assessment framework, standardized analytical methods for monitoring, establishing baseline occurrence data of microplastics in aquatic ecosystems, and figuring out how those particles are getting into our ecosystems, then recommending source reduction strategies. A key component of both of these bills is developing a standardized analytical method for monitoring and for sampling of microplastics, as well as accrediting qualified laboratories. When these bills were passed, there were no standardized analytical methods for microplastics. So we developed our own and validated their performance with the help of 26 volunteer laboratories from 7 countries, as well as 2 methods using FTIR or Raman spectroscopy. We developed this method not only for drinking water, but also much more difficult matrices, including ocean water, fish tissue, and sediment. We evaluated the method performance as well as the strengths and weaknesses of these different methods in terms of their cost, as well as how long they take to run. And we found that it's necessary to use a spectroscopic technique to be certain that the particles you're finding are indeed microplastics. With just guessing at the particle under an optical microscope gets you about a 44% accuracy rate. Infrared and Raman spectroscopy are not cheap instruments, though, costing between $550,000 and $337,000, depending on the type of instrument. The consumables for these instruments are also non-negligible, and what's really important to understand is that these methods can take a very long time, especially if you do not use automated techniques. An average of 10 hours per sample for infrared and 15 hours per sample for Raman. Laboratories who wish to become accredited for one of our 2 standardized analytical methods can do so through the Environmental Laboratory Accreditation Program, or ELAP, which is part of the State Water Resources Control Board. Note that laboratories need not be based in California. They can be based in any part of the world and be from any sector. A key component of what we found in our study is that we need not use one method for all types of analyses, as Raman and infrared and the other available methods in the literature are complementary in the types of particles that they can reliably detect in terms of size, the color, as well as the polymer type, and different methods may be used in different circumstances. An example of how this might be done in practice is through our proposed tiered monitoring framework, where one could use a fast and inexpensive tool such as Nile red fluorescence to identify likely plastic particles in certain samples. And then above a certain threshold, they would then go and use a more targeted method such as pyrolysis GCMS to get the mass of the plastic particles, or using our FTIR and Raman. This framework is very similar to another tiered monitoring framework that has recently been developed for per and polyfluoral alkylated substances, or PFAS. Next, I'll be speaking about what we did to evaluate the health effects of microplastics, both for humans through drinking water and for aquatic ecosystems. To evaluate the health impacts of microplastics, we convened an expert workshop and screened the literature, asking these key questions. Which dose metrics predict toxicity? Are there certain particle characteristics associated with harm? What are the adverse effects and can we predict them? And do we have enough information to come up with a threshold or a threshold framework for regulatory guidance? Our expert work group identified three main ways that microplastics can be hazardous to both humans and aquatic organisms, including the chemicals that are bound to these plastics, biological means, as well as particle-based means of toxicity. There are over 10,000 known chemical additives used in plastics, of which 2,400 are considered to be hazardous. Unfortunately, 53% of those 2,400 are currently unregulated in one or more parts of the world, and we lack scientific references for approximately 11% of those toxic substances. In addition to chemical additives, microplastics can also act as a vector for pathogens as well as an enrichment hub for antibiotic-resistant bacteria. We've found that the co-exposure of microplastics with certain viruses can cause excess mortality, more than just the virus or the microplastic particle alone to select organisms. While we are indeed concerned about the chemical and pathogen-based hazards of microplastics, the most reliable evidence that our expert group found was for the particles being toxic themselves. For the evaluation of human health impacts via drinking water, we found 29 ingestion-based in vivo mammalian microplastic toxicity studies, of which 12 were deemed fit for purpose for expert review. The most reliable evidence that we found from these 12 studies dealt with male reproductive impacts, all in rodents. We found consistent impacts across multiple studies, with 4 different studies showing negative impacts on sperm deformity, 2 on sperm count, and 2 on lower testosterone, with some additional studies pointing to male reproductive impacts occurring from these particles. We also found 2 reliable studies indicating potential harm to the female reproductive system, 2 that affected body weight, and 1 study showing impacts to the liver. Despite this evidence, our expert work group was not able to derive levels for regulatory use. This is due to the lack of an adequate effects database. In particular, most of these studies were not doing a very good job at characterizing the particles they exposed the organisms to. They were also using a very limited subset of polymers, shapes, and sizes, mostly polystyrene spheres around 5 micrometers in diameter. We also are uncertain regarding the effect mechanisms of these particles, which is necessary for the extrapolation to the diverse particle types that we are all exposed to. And finally, we have an incomplete exposure data set with limited information on what's in our food and no harmonized drinking water data that we can rely upon. In terms of assessing risks to aquatic organisms, here we were dealing with far greater number of studies, 167 in total, with documented effects on 117 species. Unfortunately, the vast majority of these studies were not deemed to be reliable according to our quality standards. Of these, only 22 studies and 16 species were considered to be useful, which then underwent additional expert review. We then did a little bit of data alignment to make sure that we could compare apples to apples, so to speak, and then performed what's called species sensitivity distribution modeling to estimate harm to aquatic ecosystems. A species sensitivity distribution looks like this, where you line up your species based on the concentration that affects them, with the most sensitive species on the lower end of the curve and the least sensitive species on the high end of the curve. With modeling, you can then predict the concentration that would cause an impact to 5% of species, for instance, or a different value that one could select. Using this approach, our expert work group derived toxicity thresholds corresponding to 4 different management levels of concern and action. At the lowest level here, we would recommend investigative monitoring to further investigate the issue, with the highest threshold considered to be more certain in terms of the severity and the likelihood of impacts occurring to the ecosystem, in which case we would recommend that source control measures be taken. We derived a set of thresholds for a common mechanism for which we have reliable data, which is food dilution, in which the particles are taking up space in the organism's gut so they can't get food from other sources, as well as tissue translocation mediated impacts, whereby the particles are accumulating in the tissue of these organisms and causing cytotoxicity and inflammation. It's important to note that the thresholds that I just showed you are applicable to the types of microplastics that we see globally in aquatic ecosystems. And the particles that may occur in your specific water body of interest might look quite different, in which case the thresholds are going to appear quite different. You may also be interested in different types of organisms for your specific ecosystem. So we made a tool publicly available that I'm showing here. This is the Toxicity of Microplastics Explore application, which allows one to derive custom thresholds for an aquatic ecosystem of interest. Showing here just how quickly one can filter and select the values, as well as align the particle-based toxicity thresholds to your specific ecosystem. And boom, you have your own species sensitivity distribution that you can then use to assess risk. In addition to being a data visualization and threshold development tool, Tomex is also a living database of toxicity information for microplastics, for which anyone can upload published data to that will then be reviewed by external reviewers. Currently, we are working on updating this with a large group of collaborators, and for Tomex 2.0, we've added 22 additional studies for human health, as well as 125 new studies for aquatic organisms. This brings the total data set up to 12,500 data points for in vivo toxicity studies for aquatic organisms, making it by far the largest repository of information for microplastics on toxicity. Now I'll talk briefly about what the State Water Board is doing for its plan for 4 years of testing and analysis of microplastics in drinking water. Microplastics can make their way into drinking water sources through many routes, including terrestrial emissions, atmospheric deposition, and emissions from municipal and industrial wastewater effluent. Once microplastics make their way into a drinking water treatment plant, they may be removed by the treatment processes. For instance, flocculation and sedimentation are going to remove microplastics down to about 5 microns or so, and our analytical methods are only reliable down to about 20 to 50 microns, depending on the technique. This means that if we were to look for microplastics in water that's been treated using one of these techniques, it's unlikely that we'll be able to actually detect those particles. However, there still may be particles that are getting to the consumer, and especially the particles that are smaller than 10 micrometers. These are the ones that we consider to be toxic to human health because they can translocate tissue and accumulate in our organs. Understanding this limitation of our standardized methods led us to the development of an iterative monitoring approach for testing microplastics in California's drinking water supplies, in which we are going to mostly be focusing on the source waters for the first 2 years, it's shown in phase 1, and looking for microplastics in treated drinking water starting in about 2027 or so, once we have additional, more sophisticated methods that might be able to get those particles that are breaking through the treatment processes. A key aspect of this monitoring campaign is ensuring the data we receive is reliable and interoperable, which is why we developed an open source harmonization portal and database called One for All, which ensures that laboratories only submit data that meets California's standards. I'd like to talk briefly about how we applied the aquatic ecosystem thresholds to monitoring data received in San Francisco Bay, California. We compared surface water monitoring results of microplastics in San Francisco Bay to our aquatic ecosystem thresholds and found that the majority of samples within San Francisco Bay exceeded the investigative monitoring threshold, suggesting that there may be potential risk occurring in this ecosystem. The State Water Board is currently evaluating this risk assessment and determining whether or not we should place any of these water bodies on the Clean Water Act's 305B list, meaning that there's not enough information to determine beneficial use support, but there is information that indicates beneficial uses may be threatened. To meet the requirement of Senate Bill 1263 to develop a statewide microplastic strategy, California's Ocean Protection Council adopted a two-track approach in 2022 involving solutions that no-regret solutions that can be taken today, such as pollution prevention, pathway intervention, and outreach and education, as well as science to inform future action, including monitoring, developing risk assessment thresholds, evaluating sources and pathways, and evaluating new solutions. None of this work could have been accomplished without the microplastic community's commitment to free and open sharing of data, tools, and resources. If you'd like to learn more about these open resources, you can find them on a website I created called plastiverse.org. Thank you all for your attention. I look forward to connecting with you further, and happy Earth Day.
Next, we will hear from Dr. Amy Suida and Dr. Shannon Gowans, who will share their research on microplastics in aquatic ecosystems. They will also discuss a campus-wide project at Eckerd College to reduce single-use plastic consumption and will share ideas on how others can start similar initiatives.
I'm Shannon Gowans.
And I'm Amy Suida. We're professors of marine science at Eckerd College, and together we run the Microplastics in Tampa Bay Monitoring Project to research what's going on in our own backyard.
But just knowing what's out there doesn't solve the problem. So we started a project to look at plastic consumption, and with the idea that if we could change our college campuses' approach to plastic, if we focus on reduction, then if it's never used, then the plastic never becomes pollution. So today we want to tell you a little bit about our monitoring program, but really focus on the reduction side and share with you a citizen science tool that we've developed, a mobile app that will allow you to become part of the solution.
We want to tell you a little bit about our monitoring project. Tampa Bay is the largest estuary in Florida, and it receives a lot of commercial shipping traffic. Our monitoring program samples at 7 different stations around the bay. At each station, we collect 5-gallon buckets to sample very small particles. Typically, we cannot see these particles with the naked eye, and we collect these particles on filters. At first, they appeared just like a bunch of detritus or dirt on the filter, and it's hard to find the plastic pieces. So we stain those particles, or we stain those filters, and then we can pick out the plastics like those glowing pieces that you can see in this image. We also use a net tow to collect larger pieces of floating plastic from the surface. These pieces are in lower concentration, so we need to sample a larger volume of water. And this is what we use this Newston net for. In the net, we can see some particles with the naked eye, but we also stain those particles to confirm that they're plastics. We've been sampling in Tampa Bay since 2017, and Tampa Bay is a well-mixed estuary, and so far we do not see any clear temporal or spatial patterns. There are likely a variety of complex forces that influence microplastic concentrations that can only be revealed with long-term data sets.
As scientists, we do value the research about microplastics, but just documenting what's out there does not lead to a solution directly. At Eckerd College in St. Petersburg, Florida, we saw an opportunity to foster behavior change in our students, staff, and faculty, promoting reduction as the solution to plastic pollution. So the Reduce Single-Use project was started in 2018 and included 3 interconnected initiatives. The first initiative involved providing alternatives to single-use plastic, which helped break down the barriers for plastic use. So we provided items like bamboo utensil sets and water bottle filling stations around our campus to encourage everyone to be refusing single-use plastic. We also educated the community through cleanups, classes, and invited lectures so everyone knew about the problem and what they could do to be part of the solution. Finally, this all built a groundswell of support that led to us to change campus policies. So in 2019, the Eckerd College president signed the Break Free from Plastic commitment to reduce the use of single-use plastics on our campus by no longer using college funds to purchase unnecessary single-use plastics. This commitment was signed in 2019 and then reaffirmed in 2022 after COVID. Another activity that we initiated were week-long plastic reduction challenges, where community members were encouraged to record each time they used and refused a single-use plastic item. Students immediately asked, "Is there an app for this?" But there wasn't.
There are lots of plastic reduction pledges to sign online, but they're typically one and done activities that are easy to do in the moment, but as there's no long-term engagement, they rarely lead to behavior change. There are also several apps to record where plastic pollution is found, but we wanted to reduce pollution, not just document where it is. We initially developed a prototype app that allowed users to simply tally when they used or refused plastic items. The app was a bit clunky. However, it showed us that something like this could really work.
We now have Remora, a freely available app that works on Android and Apple mobile devices. The QR code will take you to the Google Play and Apple app stores. Within Remora, individuals can track their use and refusals of plastic items and see their progress over time. Remora also incorporates gamification through things like leaderboards, so you can compete for the top spot each week. We can also devise challenges for smaller sets of users to compete against themselves as well. Users can also earn badges for milestones for things like a 10-day-long streak, or for refusing 100 or even 10,000 single-use plastic items.
Hi, and welcome to Remora. My name is Carly, one of the Remora interns, and today I'm going to be showing you how to make a post on Remora. Let's get started. To first start your post, click on the blue plus sign at the bottom middle. Switch between I refused and I used categories depending on if you refused or used the single-use plastic item. Scroll through the categories to help you locate items easier. For our purposes today, we will be refusing a single-use plastic straw. However, we will be using a plastic cup and lid. Add or subtract quantities of items as needed depending on how many you used or refused. Then in the upper right-hand corner, click on Next, and you're almost ready to post. Now add a caption. Today we could say this is from our smoothie that we drank earlier. Then click on the blue Add Location button to add the location of where you used or refused these plastic items. Remora is a program through the Reduce Single-Use team at Eckerd College, so we could say we drank the smoothie at Eckerd. Then in the same upper right-hand corner, click Share. Now your post is all complete, and go to your profile to see your new post along with previous posts. Click on the global feed to view other people's posts and the home button for your weekly progress. We can do more with less.
Not only does the app encourage users to reduce their plastic consumption, but user data is combined to create a database that can inform government policy and transform business practices.
This is similar to our work at Eckerd, where we were able to demonstrate that the community would support a commitment to break free from plastic. With the Remora data, these transformations can be expanded on a regional, national, or even global scale.
Here are two examples of Remora data at work. St. Petersburg, Florida implemented a plastic straw ban in January 2019. Is the straw use lower in St. Pete? We thought we'd ask this question to see how we could explore it with the data. You can see that plastic straws are still being used in St. Petersburg at similar rates to surrounding areas. Really, when you go out and about in St. Pete, the default is to distribute straws, making refusal pretty challenging, especially at restaurants. And there's also been a targeted marketing of bioplastics in the city, and it's pretty counterproductive to the ordinance. We see these straws all over the place.
So another question we can look at is comparing by business type to see where it's easier to refuse single-use plastic. So again, if we look at the data, what we can see here is that how frequently the Remora community is able to refuse plastic does vary by the business type. When the community goes to shops and restaurants, gas stores, that kind of thing, what we see is that very often people are actually accepting the plastic that's being given to them. In contrast, when we look at supermarkets, we see that we're logging the smallest ratio of uses to refusals. So what this suggests is that the Remora community is thinking ahead before they go to the grocery store and taking their cloth bags with them. So refusing plastics in a supermarket is likely to depend on that individual action of taking the plastic bags with them rather than the business practice. It doesn't have to be that way. We can encourage businesses to transform their practices so that maybe you get a reminder the next time you go to the mall or go to a home repair shop to take your cloth bags with you. So I've always come from a scenario where I've bridged doing the scientific research with combining it with advocacy and policy. My background is working with endangered marine mammals, so it wasn't enough to just document how many there were and what kinds of threats they were facing. I was always drawn into how do we protect them, what kinds of policy changes need to be done. So the transition with working with plastics to move from just documenting the microplastics work to the education, outreach, and advocacy work was a natural for me.
And for me, it was a little bit different. I started in a career in plankton ecology, and my work is not so accessible to the public. So it was all about writing scientific papers and sharing the knowledge in that way. But then I did start to transition to plastics, and I remember having the conversation with fellow scientists about whether it was okay for us to be advocates and to sort of help educate the public in that way rather than through our scientific work only. And there was question about that, but then I actually started to see colleagues who I admired start to stand up and speak up about climate change and about plastic pollution and other pollution, and it really inspired me to do that in my own work and really apply my science to questions that are really important for society to answer.
And we can still be objective scientists, so our microplastics monitoring is still very much that objective science of what is out there. Our opinions about plastic aren't driving our findings, but it's what you do with that information that's where you can move into that advocacy and change piece.
And it sort of helped us as we looking at the plastic in Tampa Bay and seeing that it was here and wanting to let the community know what was there. It was a natural transition for us to start trying to get the community to make change. If we don't put, as we said at the beginning, if we don't use plastic, then it won't get out into the environment. It's not to say that we can't use plastic at all, but we need to find ways to reduce the amount of plastic that we're using, and especially the unnecessary plastic.
And we found our students are especially they find this approach appealing because they're looking at all of the challenges that we have in the world, and they're really trying to figure out their place and how they can not only be scientists but also be making the world a better place.
So should we Look forward to
seeing you on Remora.
Our final segment features the winning submission of the 2023 Earth Science Week video contest, in which student Toby Lang discusses the potential for ferrofluids to be an innovation to remove microplastics from the environment.
This is a microplastic. Although most invisible to the human eye, it's all around us, from the clothes we wear to the food we eat and to the air we breathe. These tiny fragments of plastic, less than 5 millimeters in size, result from the breakdown of larger plastic debris. Their small size allows them to be easily eaten, from the smallest plankton to the largest whales. These microplastics can absorb and carry pollutants, causing damage to the organism. These unavoidable materials can be reduced, however, with just a bit of innovation. Introducing ferrofluid. It may not seem like much in this glass bottle. Comprised of tiny magnetic particles suspended in a carrier fluid, it's able to bind with microplastics, making them easier to capture. Its effectiveness, however, strides far over than just a small bottle. It's able to clear a whole ocean. By introducing a magnetic field, the ferrofluid, which is now bound to the microplastics, is attracted to the magnet, allowing for an efficient and effective removal process. But why is this significant? The beauty of using ferrofluid is the precision and selectivity they have in targeting microplastics, which can be otherwise challenging due to their minuscule size. Additionally, once the plastics have been captured, it can be separated from the fluid, allowing for the process to be sustainable and environmentally friendly. The world is changing all around us. Ferrofluid itself may not be new, but new applications like this are always discovered. Perhaps in the distant future, new applications for a different technology can be utilized to change the world for the better. This is a
Great, thank you all for your presentations. It was great to hear about microplastics and the work being done around the country. Lindsay and I are excited to talk about your work with you. Just as a reminder for those listening live on April 19th, please add your questions in the chat and our speakers will be able to interact with you online. All right, now we'll jump into our panel discussion. We'll be asking each speaker a question about their presentation, and our other presenters can also jump in and add information. We'll start with our first webinar speaker, Maya. You discussed that there are microplastics in the air. Can you elaborate how they get there?
Sure. So it's important to remember that microplastics are really small, which means that they can be very buoyant in the air. So these microplastics can be coming from a number of sources. They can be any synthetic material that gets rubbed against in some way, shape, or form, causing it to fracture and break off little pieces that then can get carried in the air. That includes our laundry system, especially our clothes drying, but also simple things like walking on a shag carpet or sitting on a chair or wearing a piece of clothing.
I'm envisioning right now my 2-year-old running around on a very fluffy carpet in our room. Just things that we need to get cleaned out of our air now. Awesome. Does anyone else have anything to add about microplastics in the air?
Yeah, I'll just add that when it comes to information about risks to humans about microplastics, the earliest conclusive evidence that microplastics can be associated with health outcomes, adverse health outcomes in humans, actually comes from a study focused on air and inhalation. Back all the way in the 1990s, late 90s, there was a case of an occupational hazard exposure to textile fibers in a flocking facility in Rhode Island. And they found that the workers that were exposed to high levels of microfibers had a 3-fold level increase in lung cancer. And this was found conclusively to be caused by these microfibers, and not just the fibers themselves, but they found that there was an additive toxicity happening with the chemicals that were added to the fibers. So this is a further field of research when it comes to the exposure that we all have in our homes, so non-occupational hazard. But yeah, this is really before even the term microplastics was coined. We knew a bit about inhalation and toxicity to microfibers.
Well, expanding on that, our next question is for Melissa. You mentioned that equipment is made of plastics. And so are microplastics coming off of that equipment and other everyday plastics? And if so, what are some examples?
So, yeah, this is a really tough question to answer. It's plastics are everywhere. And so as science has moved forward, you've used a lot of plastics in our equipment, from pipettes to our laboratory settings. We have trouble, like when we started working on microplastics, we went into like, okay, so what clothing are we wearing? What equipment are we using? How are we handling the samples? And what's in our rooms? And it became really difficult. It became like this rabbit hole and like trying to remove it. So we do see that plastics are coming off of our equipment, off of the plastics like from the sampling locations, and we have to do a really good job of trying to separate those two. One thing that we're trying to do is like characterize what the sites are, have background samples with inside of there, and just try to, keep it down. And it's really, so we've been putting like HEPA filters in all of our rooms to try to help, or even outside of the rooms, so that you're walking into an area where we're decreasing the number of plastics that could potentially get into our samples. But it's a really tough way to be able to separate what's from the sample and what's coming from our equipment.
So, given everything you know, does everyone here have a HEPA filter in their office? Oh, some do, some don't. Okay, interesting.
Yeah, we during COVID, we put HEPA filters in all of our classrooms. And so we've been going around the university picking up those and bringing them into different areas inside of our building, since we're not using them in the classrooms as much anymore. And we had bought some ones that were all metal. And so we were using those near our microplastic analysis.
Great, thanks, Melissa. Our next question is for Scott. In your talk, you mentioned quality standards. Can you explain the process and types of studies that you would include and those that you would exclude from your critical review?
Absolutely. So when it came to reviewing studies for understanding the hazards of microplastics, we we needed to be sure that the studies that we were evaluating were both reliable and relevant for informing risk assessment. And the key bottleneck criteria that we ran up against was that many of these studies were only using 1 or 2 doses to expose their organisms to, and they were typically very high concentrations of microplastics, far above the levels that you would be finding are relevant to environmental exposures. A lot of these studies were also not doing a great job of characterizing the particles that they were exposing the organisms to. And this becomes quite relevant when we want to understand how the particles are causing harm, so that we can understand the diversity of particles that we're exposed to, and extrapolate between the particles in the lab and what we're exposed to. There's really a long way to go until we can get to a conclusive health-based threshold for human health in particular. But when it comes to environmental exposure for ecosystems, we're much closer to having a solid answer.
Yeah, it's good news that there's progress being made and it's continuing to progress. That's awesome to hear. And it is important, especially for those students listening, about the nature of science, that we're making sure we are reviewing accurate information and resources, and taking a look at different science with critical eye. So thanks for mentioning that, Scott.
And part of that progress was mentioned by Shannon and Amy. You talked about Eckerd's commitment in 2019 and 2022 to not use funds to purchase unnecessary plastics. Can you speak a little bit more about that commitment and what might constitute a plastic to be thought of as unnecessary versus necessary?
Sure. We started really with a grassroots effort because we needed to show that the community really wanted to make this change and to help the administration understand that. And so we see Eckerd as this microcosm of the entire country or the world. And so as students and staff and faculty at Eckerd showed that they were really excited about reducing their plastic consumption, then we spent a lot of time meeting with administrative units on campus to gain commitment from them and to talk with them about how they could help from a top-down perspective, help the people that work with them to think about reducing their plastics. So we followed the Break Free from Plastic pledge that had been put out there as an opportunity for colleges to make those changes, but then adapted it really to Eckerd. And we implemented it in 2019, but then reaffirmed it after COVID. What do unnecessary plastics mean? It really, a lot of it came down to focusing on food and food service. And so looking at athletics and thinking about reducing water bottle consumption and bringing, reusable containers with water to events, thinking about how we serve in the dining hall, though that's working with catering services here on campus who have tried to make lots of changes. And then also with the bookstore, not having plastic bags, asking people to bring their own bags, or supplying paper bags when necessary. So it was the small things that we use a lot of, and trying to make sure that we could find replacements for those and make that sort of the everyday way of things on campus.
But
That's
of course
really
we
great.
want.
Oh, go ahead. Sorry.
But we wanted to recognize that there are certainly some plastics that are really critical that we do continue using. So we have a health services on campus, and of course we want them to have all of their materials sterilized, and a lot of that does at this point need to be wrapped in plastic, so that is not covered. We also know, as Melissa mentioned, a lot of the tools and equipment that we use, even things like in our microplastics monitoring, we use Petri dishes, which are plastic. Our fibers, our filters are plastic. So again, we left those kinds of things as necessary, as those plastics that could still be used. Hopefully, as we get better and better products that are avoiding plastic, we can expand our definition of unnecessary plastics. But this was a really good first step to cut out a lot that's really very easy to refuse.
I definitely agree. That is a great first step. Do you have any insights so far onto the effectiveness of the initiative, or any impacts that you've noticed in the college community?
So we made a lot of progress before COVID. And then we took many steps backward during COVID. But it really was seeing changes in what our dining services was doing and offering, and seeing where students were choosing to bring their own cups or bowls or utensils with them around campus. We supplied, as part of a grant that we had, we supplied the entire campus with bamboo utensil sets. And so we would see those around campus and people using them instead of taking disposable utensils from the pub on campus. And so we did make a lot of progress with COVID. There were many steps taken back. And so we're working our way back toward that. But we had made measurements and observations outside various locations where disposables were used a lot, and saw reductions in their use. And so we're hoping to get back to that point again soon.
The other thing we see is a lot of great conversations are happening where people are trying to figure out, okay, does anybody know what a plastic-free alternative is for this product? How can we band together and pool resources? So, our athletics team used to use a lot of balloons for decorations for games. So how can we instead, perhaps with a more upfront cost, to get some heavy-duty reusable ones that can replace those disposable ones? And as we are going through those conversations, we can actually see cost savings, which is creates that double win for us.
Great, thank you guys. And speaking of alternatives, Maya, can you speak more about the biodegradable plastics and bioplastics that you had mentioned in your presentation?
Sure. And this is an area where I encourage people to do their homework when they're hearing about and considering purchasing products that are labeled as biodegradable or compostable. The term bioplastic simply means that the stock that it's made from, the source that it's made from, is something biological. Well, petroleum is biologically based too. So a lot of the terminology doesn't really mean anything, and it's important for people to be aware of that. But where there are areas of where I think scientists are hopeful is using some sources for bioplastics that are actually based on bacteria. Bacteria have this energy storage compound that can be extracted and utilized to make what's commonly referred to as PHA plastics. It's a really long name that I won't try and say. But those plastics do seem to be able to be almost customized to actually degrade under particular environmental conditions. So the good part of that is they could actually biodegrade back to their elemental components, which most other plastics will not do in a reasonable time period. But the bad part is the plastic then has to be disposed of or put into those particular environmental conditions. And that's true for the plastics that are labeled as compostable as well. They can be certified as compostable, but what that means is they have to be put in an industrial or commercial composting facility, which exposes them to high heat plus oxygen plus moisture. And it still takes a period of time for them to actually compost into a product that could then be used in that way. But I would say the large majority of the country does not have access to industrial or commercial composting facilities. So what happens to those, green labeled plastics? They end up going to the landfill where they last just as long as non-compostable plastics because they're not in the right conditions to allow them to degrade.
We made a conscious decision with our commitment to not use college funds for plastics to not include those biodegradable plastics, again, because we do not have an industrial composter in the nearby vicinity. If we were able to have one, then we can switch those and alter those regulations. But as Maya mentioned, it really is still just plastic if you don't have the right way of breaking it down.
Are there any organizations or companies that are helping facilitate that process? Like, I have biodegradable plastic, come pick it up, or does that not exist yet at this time?
I mean, I know that in some areas where the commercial composting facilities are available, there are ways for people to get their materials. They can put them out. I think in Seattle, they can actually put them out as curbside recycling in a separate container to go to the composting facility. But here in Florida, we don't have the facilities, period. So it doesn't matter how far you live from Miami or Gainesville or Tallahassee, the facilities don't exist.
Can I also add to agree with Maya about the sort of labeling of things? Those PHA plastics are labeled at times as marine biodegradable, and yes, they may meet a certification standard, but if they make it into the marine environment, they are lasting for extended periods of time as the product that they are. So there are any number of biological implications for that. So they're not dissolving right away in the marine environment when something is labeled as marine biodegradable.
It's interesting. I hadn't heard that one before. So we know that the plastics are in the environment, and we know in particular that weathered microplastics are more mobile. And Melissa, you spoke about this. Is this a bad thing, or could the charged particles actually be easier to clean up?
Yeah, so one of the things so once these microplastics get into the environment, they're weathered. And then we're talking about, biodegradable plastics, they're all going to get weathered the same way. And so their charges on the outside surfaces change. So microplastics can absorb. So we use the term absorption, which means either absorb, so like take in like a sponge, or adsorb, which is kind of like more like a magnet. So plastics can, like when we have spaghetti sauce instead of something plastic, it turns red because it's absorbing it. So as the plastics are becoming weathered, they're getting more charges on the outside, just like our soil particles. And if they move more through the environment, they can actually get into our drinking water supplies. They can get into our environments a lot easier. So a lot of times for like remediation or cleaning up things, we want to kind of hold it in the area so that we can then clean it up, in that area. The student who won the award for the best talk, who's talking about ferrofluids, well, if we are changing the particles for absorption, we're going to be changing maybe how well those type of fluids might actually work. Also, when we start thinking about using like ferrofluids, if we're doing remediation, we do what's called pump and treat in groundwater systems, where we pump up the groundwater, we treat it at the site, and then we re-inject. So if we have the plastics nearby and we're using, say, some sort of treatment, I have, ferrofluids could be an example, we could be keeping them where they are. We don't want plastics to be mobile to make it easier for them to biodegrade. We want to keep them nearby in there.
Great, thanks, Melissa. Our next question is for Scott. Can you speak more about the capabilities of the Tomex website? Is this somewhere a user could go to learn more about water in their area, or is it more geared towards users that are already aware of what is in their water and using the application to examine thresholds?
Thanks, Lauren. So Tomex, or the Toxicity of Microplastics Explorer, was an application that we built to support the development of health thresholds for human health and ecosystem risk. And right now, it's really geared towards regulators and risk assessors and scientists to better understand where we're finding effects, predict effects for their specific ecosystems, and even come up with thresholds themselves. It's been used by governments around the world to get a better handle of where they might be finding effects in their specific ecosystems. It can be used as an educational tool as well, just to understand a bit more of the complexity and how these different factors, particle factors, can influence the toxicity. But if someone wants to learn more about microplastics in their water or their environment, or what folks are doing in their particular region, I would encourage them to visit plastiverse.org. This is a website that I created with friends to pull the diamonds out of the rough, so to speak, in terms of databases and resources that are publicly available, and make them easy to find for educators, scientists, students, any curious minds. Right now we have over 150 resources on there, including where to find information about microplastics in your region. One other thing that I would mention for folks that are perhaps educators or want to learn more about plastic pollution in general is the Wayfinder program, which is run by the Algalita nonprofit based in Long Beach. They've been running for decades around the plastic pollution issue, and they have an amazing wealth of resources for educators, curriculum. They also do a lot of live and virtual events.
Great, thank you. And Shannon and Amy, in your experience, what are some of the most effective strategies for engaging students and community members in sustainable practices and behavior change regarding to single-use plastics?
So one of the things that we've clearly learned, which is not really surprising if, to anyone who's in education, is that you can't just mention something once. It really takes that sustained multiple approach. People have to really be interacting and thinking about their behavior and how it can make a difference, both positive and negative, over a longer term. So one of the things that we found with our project is that when we were first looking at what are resources out there, we saw lots of plastic reduction challenges or pledges, and most of them really were a button that you click on a website and you say, yes, I'm going to reduce my plastic, and that's all it was. Or you might get put onto an email list and get sent out more information, but there really was no accountability or sustained interaction.
So we wanted to build in this idea of students really thinking carefully about what plastic they were using and when they were able to refuse it. So we started off with one of our first classes with a plastic reduction challenge where we wanted students to just record when they used and refused plastic. And we gave them a piece of paper to record it, as we mentioned in the video. And their response was, isn't there an app for this? So that's how we did develop this app, Remora, which provides that sustained continual interaction with using and refusing plastic. So people are thinking about it on a regular basis. The other thing that I think is really important to working with people for that kind of behavior change is we don't need a few people using no plastic. We need a lot of people using less. And if we keep using less, then we can get these changes happening. And when we create that groundswell of support by the community saying, we don't want to be using these products anymore, then we can go to policy or business practice level changes, which brings everyone else on the community on board. So it's really that community support and multiple interactions, multiple touches that really start to make a long-term difference.
Great, thanks, Shannon. Now let's talk about that Earth Science Week contest winning video. Melissa brought it up briefly about the ferrofluids, but I'd like to open this up to all of our presenters in that the student discussed how ferrofluids can be used to clean up microplastics. Does anyone want to share their thoughts on that technology for cleaning up microplastics and if that's a reasonable solution or kind of the science behind how it works?
I guess I'll kick things off. So I think ferrofluids have been shown to be a reasonable way to remove microplastics from aquatic settings. This has been done in the lab. There have been a number of papers published on it, trying different oils as the sort of the base for the fluid part for the ferrofluid, and of course you've got to have the magnetic metals added to it. I think the challenge comes with taking something that works well in the lab and figuring out if it's A, feasible, or B, has any potential negative consequences in the environment. So normally we think about, oil and the environment, those two not being good together, that oil's not necessarily, it's usually going to have negative impacts on especially an aquatic environment. And so that's where challenges could come in trying to implement something that works well in the lab in the field.
I agree, and I think it is the challenge of taking something small scale to large scale, and I think we've seen this with the ocean cleanup as this proposal to clean the whole oceans of plastic that evolved and has evolved over time and has had failures and has removed a bunch of large plastics from the ocean, but has had many challenges along the way. And so I think we see this also, I think, with climate change mitigation as well. And it's how do we scale up to have an impact globally? And maybe it's not possible, maybe it is possible, but it's thinking about the best ways to do that without introducing potentially more impacts in the process.
Yeah, I'll just add that we've seen this happen time and time again in environmental cleanup efforts. The Deepwater Horizon oil spill was a case where they applied a chemical dispersant to try and deal with the oil that was on the sea surface. And what we found in toxicology tests later is that the dispersant actually makes the carcinogenic components in the oil more bioavailable to the fish. and so it increased the risk to those organisms. So I would hate to see something similar happen with an environmental exposure to something like ferrofluids. There may be potential applications where it makes sense. I've seen it used. I've seen a couple papers using in wastewater treatment plants, where in that case it could be highly controlled, much more likely to capture it before it leaks out into the environment. But along those lines, some of the studies have found a lower efficacy of removal with the ferrofluids compared with more conventional treatment methods, such as filtration techniques.
Great. Well, thank you so much for sharing all of your expertise today. That's all the time we have, unfortunately. So we want to thank you all for being here and hope that this was an informative kickoff to the Earth Day celebration of the theme Planet versus Plastics. We at AGI thank you for attending our Earth Day webinar and want to extend our sincerest gratitude to our presenters for their work on critical issue of microplastics. As we commemorate Earth Day, let us not limit our appreciation for our planet to just one day a year. I invite all of you to continue exploring and celebrating Earth's wonders all year round. And in October, be sure to join AGI in the celebration of Earth Science Week 2024, which will highlight the theme Earth Science Everywhere, for which we produce free educational resources, including our Earth Science Week Toolkit and additional webinars, one of which will be dedicated to further exploring the pervasive issue of microplastics in our environment. Together, let's strive to make every day Earth Day and every week Earth Science Week to work toward a sustainable future for generations to come.